Okay, let's do it. Okay, hello everyone. Welcome to webinar 12 of AM Smart. We have another session, and again on the topic of the smart material, but this session is different because the topic is about the smart materials, specifically magnetic smart materials. And I know some people already in the attendee list, they are working on this topic, or at least they are interested. The host of this meeting is my colleague, Professor Moataz Attallah, and he is already in the new university, Loughborough, and in UK. He's Dean of the Engineering Faculty. I'm very happy he accepted in the busy schedule to be a part of this meeting and host it. And we have two great speakers here. I will leave it to Moataz to introduce them. And I hope you enjoy the talk today with two nice presenters. And in the end, I add a couple of comments about upcoming webinars and also conference. Thank you very much. Moataz, floor is yours.
Thank you, Mershad. Hello, everyone. I'm very, very thankful for Mershad for giving me the opportunity to chair this session of the Smart Materials webinars that he has been holding, or the additive manufacturing of smart materials webinars. It's a great initiative because this is a relatively small community, but it's once we are together, this is when we realize actually that the community is getting bigger and we have a lot of people who share the same interest. And this hopefully will be the nucleus of opportunities that we can work on together, whether it's research funding or even looking into outreach to explain the potential impact of this technology to many people in the industry and elsewhere. I'm very pleased today to be joined by two of the most, how can I say it, active early career researchers in the field. Two people, I hope one day, we hope to see them as the future leaders of the additive manufacturing of smart materials. And it's actually a great thing that we're trying to promote early career researchers who have been active in this field. The first speaker today is Ville Laitinen from Loughborough University of Technology in Finland. Ville indeed has been one of the pioneers, if I can say so, of laser powder bed fusion of nickel manganese gallium work. This is the baby he started a few years back, and he has been growing, looking into it as it grows in multiple activities. Of course, this is in a great university where there has been a significant track record on nickel manganese gallium shape memory alloys in general, looking into them initially as single crystals prior to moving into working on additive manufacturing. So Ville, very pleased to have you today, and I'll be looking forward to hear your exciting work. Please start. Thank you.
Yes. All right, let's first share the screen and start this. You can see the screen? Perfect. So thank you for the introduction, Moataz. Yeah, as Moataz mentioned already, I work from Lappeenranta, Finland. I'm working in a team that is in the really core of magnetic shape memory alloys. So our group leader, Professor Kari Ullakko, is the person who originally found the magnetic shape memory effect during his stay in MIT in mid-90s. And he's been working on this already past 30 years. And at one point, we started moving from this conventional single crystal materials towards a little bit more advanced materials approaches. And my work on laser powder bed fusion is one of the core in this topic field. So a little bit background. So what do we mean by magnetic shape memory alloys? First, we have conventional shape memory alloys, which of course have this effect of shape memory effect and superelasticity that are based on this low temperature martensite, and especially its ability to form martensitic twins. And the core phenomena that happens in martensite is that through this twinning, they can dissipate a lot of shear forces in a manner that provides a plastic deformation, but a deformation that is fully reversible. Of course, in shape memory materials, conventionally, this is used in a shape memory effect where you have then, by heating this martensite to higher temperature austenite, then you can recover some previously trained shape. Or if you have a superelastic alloy, then you can, by stress-induced phase transformation from austenite to martensite, you can have this local plasticity, and then by the removal of the stress, you can again have the shape recovery. Now, in nickel manganese gallium in particular, which is one of the most used and well-known magnetic shape memory materials, we have also a third phenomena going on. And this is called the magnetic shape memory effect, which can produce approximately 6 to 12% magnetic field induced strain. Okay, here. So magnetic shape memory effect, you can see on this right side video, that's actually a nickel manganese gallium single crystal in an electromagnet. And where you have this marking F with the arrow, that's spring-loaded pressure. So by external magnetic field, we effectively elongate this element. And then once the field is removed by the spring force, we are bringing the element back to its original configuration. And how this effect actually happens is that we have nickel manganese gallium martensite. In this case, in this figure, we have a 10-layered modulated martensite, which has, if you consider in the original cell of this L21 austenite, it's actually tetragonal cell. And this tetragonal cell have axes A, B, and C, which A and B are approximately equal to each other, and then the C axis is shorter. But what is nice with this material is that we have these manganese atoms placed by nickel and gallium in just the right distances from each other that we actually have a magnetic moment on those manganese atoms. And this material effectively becomes ferromagnetic, and this C-axis, the shortest crystallographic axis, is also the easy magnetization axis. And it's characteristic to this material that the magnetic anisotropy energy is significantly larger than the energy required for moving crystal boundaries, these twin boundaries between different martensite variants. So what happens when we bring this external magnetic field is that this C-axis starts to exhibit magnetic field into stress, which tries to pivot the C-axis direction in the direction of the external field. And this provides a pressure to these twin boundaries to be moved around. And since other variant, which is in a preferred orientation, grows at the cost of the variant which is not in preferred orientation, then we will actually have a physical change in the material because of this flip of crystal orientation. So effectively, if you want to simplify this idea, is that you can imagine this crystal unit cell as a magnet, and the C-axis is imagine it as a compass, and the C-axis is the compass needle. In a normal ferromagnetic material, you bring the external field. This compass needle moves in the field direction, but in this material, the compass needle is fixed to the compass itself. So when you bring an external field, the field turns the whole compass. That's essentially what magnetic shape memory effect is. Now, the main advantage of this is that, of course, that this phenomena can be very fast. So if you make a very small single crystal, you can achieve in saturated magnetic field pulses up to 2 million meters per second squared acceleration. So 200,000 Gs. That's the fastest material we have ever made. And from extrapolating from this acceleration, it's possible to make actuators that can have 200 kilohertz actuation speeds or frequencies with magnetic shape memory effect. I will cover a little bit applications also. So one of the best applications by so far we have developed is magnetic shape memory micropump. So how this works is that we have a nickel manganese gallium single crystal, which we bring under this crystal a diametrically magnetized cylindrical magnet. And by rotation of this magnet, we generate on this single crystal a tiny undulation. And by rotating the magnet, we can move that undulation across this single crystal surface. And in effect, we can use it to carry liquid. So it works in a very similar way as if human swallowing works in a throat. And for comparison of sizes, why is this so attractive is first is that we have on this right top image, we have a conventional industrial piezoelectric pump, which is used for 20 milliliter per minute pumping. Then on that 1 euro cent coin, you can see this tiny nugget of metal. That's a magnetic shape memory micropump of the about same pumping volume. So the size difference is huge. And this is one of the main advantages of it. So we can embed it, for example, in lab on chip or factory on chip kind of configurations where we have effectively the pump is a tiny piece of metal in a fluid channel. So it's a simple, and this is something that could be used for different kind of point of care applications. Then we can of course go in a more macroscopic devices. In this case, this is actually a device we developed last year at LUT. This is a linear actuator that uses train wave gearing. So we have 4 synchronous MSM elements in an electromagnet there, and they engage this kind of bar that has notching so that they engage it like unsymmetrically. It's meaning that every time one of this kind of pyramid head points that are connected to this MSM elements engages the bar, it engages it from one side in a way that it provides a lateral force. And then once the one element loses the force connection, then the next MSM element picks up from so it's asynchronous in a way, and we can produce a continuous linear motion. And next stage we want to do this is that we want to actually make it circular motion. So we will have a circle actuator coming out of this. Well, why we want to do additive manufacturing with nickel, manganese, gallium? First of all, there's a little bit of terminology. So 4D printing, many of you might heard of it before. How we see 4D printing is that it is essentially additive manufactured structures that enable externally activated shape change or other functional response post-fabrication. So if you use your additive manufacturing process parameters to tune this functional performance, then it's 4D printing. And why we want to use it for nickel, manganese, gallium is that first, although we observe the best functional performance typically in single crystals, we are very limited with geometry. So most of our single crystals are these very like stick-like features cut from a single crystals, and you can only do a limited number of devices with that kind of geometry. So that's one way. Second thing is that then, of course, we want to minimize mechanical machining in these production phases because nickel, manganese, gallium in particular is very, very brittle material. And this also because of this really low twinning stress that allows this magnetic shape memory to occur, it also deforms very easily in martensitic form. So it's very difficult to cut it into a shape. And then, of course, additive manufacturing involves very complex 3D structures and functional integration. Like we have on the right side image that's actually from Formnext a couple of years back. It's a rocket engine made with additive laser powder bed fusion process. And you can just imagine how complex things can get if you use this kind of technology. Now, key challenges is that we will produce polycrystalline in most AM processes. And this can be a challenge because grain boundaries and defects can hinder twin boundary motion in MSMAs. And I will cover this a little bit later in the slides. So process laser powder bed fusion, you are probably very familiar, so I won't be going in very detail what is going on there. The essence is that we have this powder bed in a sequential way. We spread powder and selectively melt it from above with the high power laser and repeat the process as long as we get this full 3D geometry being manufactured. Why we choose to use laser powder bed fusion in particular for this material is a couple of twofold. So first is that conventionally they have been using a lot of binder-based processes to make nickel, manganese, gallium. Now the problem with binders is that when you have this binding agent, this chemical that you bring in this process, it is very easily transmitted into the metallic lattice of nickel, manganese, gallium during this post-processing heat treatments. And if you alloy, for example, your nickel, manganese, gallium with titanium or even oxygen, you effectively ruin first magnetic properties, and then in secondary, your twinning stress starts to increase so drastically that you won't be able to move those boundaries around with external magnetic field. And then second approach why we use laser powder bed fusion is the feature resolution. So laser powder bed fusion, we can actually go and make very, very small actuators. And this type of metallic smart materials perform exceptionally well when they are made into very small devices. In this kind of very small devices, typically these conventional mechanisms and such devices, like electric motors, for example, they're very difficult to manufacture. So smart materials have a big competitive advantage there. The type of feedstock we typically use for laser powder bed fusion is usually we use argon gas atomized spherical nickel, manganese, gallium powders. Advantage with this gas atomization process is that we get very dense, these kind of circular shaped spherical particles. So these are very good for the laser powder bed fusion process itself from the spreadability point of view. And also that we are not bringing any inherited porosity with the particles themselves. Then also advantage that because it happens in an inert atmosphere is that we have typically very low oxygen amount in the powder itself. So what we have been measuring from our powders, it is typically in the range of 200 ppm. Of course, this can significantly degrade if you are recycling your powder, so you can actually start accumulating quite substantial amounts of oxygen, and that's a critical point of view from the making of functional material that you might need to actually keep a trap on that how much oxygen you are putting into your powder. But then what is the key result is that during this development, we have actually made quite a few batches of this, and it's clear that we need to actually overdose these powders with manganese because of some selective elemental losses that happen in the laser powder bed fusion. And this is something I will discuss in a couple of slides. How the process itself, when we develop, how do we work? So the basic track is usually if we start with new materials that we do this kind of single track, single layer kind of experiments just to like basically see where do we have a zone of weldability for the material, where can we achieve, for example, crack-free melting of the material in a way that we have a good wettability of our substrate material, that we actually get to make some really good welding bed without having some substantial defects in that stage already. And if we manage to make a process which works in that stage, then we can move to 3D geometry. And I think what most academia and industry likes to use as a test bench particle is different kind of cuboids. I guess it's because of the geometrical simplicity, but also because it actually allows you to have little bit simplicity in the post-processing phase, especially when you're interested in the number of characteristics, including density and magnetic properties and post-processing steps. So you remove the complexity of the geometry out of the question, then you get to focus more on the material property. Then once you have that set up, you can move to a number of different complex geometries. On the up, you can see some thin walls. We actually have made some functional materials with this kind of geometries. And then on the bottom, you can see some of more later samples we have actually made with Moataz team. Is this very complex 3D lattices. And we have also achieved some strain in those materials. So it looks very promising. Now, from a nickel-manganese gallium material point of view, we need some necessary post-processing steps, and first being the heat treatment. After the laser powder bed fusion itself, we have a huge amount of atomic disorder inside the material, and in order to recover magnetic properties, especially, we need to do a high-temperature heat treatment where we get these atoms in the right places so that we have a long-range order in our atomic lattice. We usually use two-stage heatment. So we have this homogenization treatment, which is at quite close to solidus temperature of the material. The point of this treatment is to just distribute those atoms equally within this geometry we have made. So basically, it's just a diffusion of diffusion. And depending on the times, it can be something in the range of a couple of hours treatment, or in a case of bigger parts, we might have also up to 12 to 24-hour treatment. We can also induce quite substantial grain growth in this treatment at that temperature range. And then we have the secondary treatment, which is ordering temperature. So this is just above the transition temperature from B2 unordered cubic phase to ordered L21 austenite. So the point of this temperature treatment is that we are basically setting our atoms in an exact right position just before we cool over this transition. And this is actually, out of these two treatments, this is the more important one for the magnetic properties. So if we go over this transition too fast, we lose some of our long-range order, and then we will have an inferior magnetic performance. And well, on the right side, you can see some examples from materials we have, actually nickel-manganese gallium, that has been heat treated after the laser powder bed fusion, and we can get quite nice properties. So magnetization, saturation magnetization significantly improves after heat treatment. We start to observe these normal magnetic phase transitions also, like you can see there, this with circular dashed line is actually the Martensite transformation, and then Curie temperature at higher temperature. And then we also get this magnetist like domain structure put in place. So at the bottom, you can see that's actually magnetic force microscope image of a very specific orientation of a laser powder bed fusion fabricated nickel-manganese gallium. So you can see this characteristic domain structure where you have a z-axis in the plane of the image, and then versus when z-axis is like in a 90-degree angle compared to this plane of image. So I mentioned manganese evaporation with the powders, and this is something that is very important because this manganese in particular is extremely volatile element in nickel-manganese gallium. So it has a number of characteristics. One is that its boiling temperature is the lowest among the nickel, manganese, and gallium elements. And then also its vapor pressure is in such a manner that we are very easily in a high temperature treatment, for example, heat treatment, or in this kind of high intensity process, we are selectively removing it from the equation. So it very easily leaves the lattice. And this is something that we anticipated that was happening, but the amount that we can lose is actually quite bad. So if we are really excessively bringing in laser powder power in the process during the melting, we can actually lose even 10% manganese out of there. And that's effectively, we can alloy nickel with this. We can just make pure nickel by losing all the other elements of the material. So what to do in typical optimized processing parameters, we lose manganese in a range of 0.7 to 2 atomic percent. And it's mostly at the cost of nickel. So gallium content tends to stay roughly the same. We are losing some of it, but mostly we are not losing it in a substance amount that we can actually see a big difference. But nickel tends to pick up like what manganese loses. So most of the time our powders, we just over-alloy them so that we increase the amount of manganese, for example, 2 atomic percent, and then we decrease the nickel content the same amount. And then after optimized process, we actually have an alloy which is corresponding to functional material. So we can actually make something that works. Now, this can, of course, provide a different approach. So if we use this over-alloyed powders, we have this on the map, right? You can see where the functional alloys, it's very small compositional zone where we can achieve them. If we make a powder that is over-alloyed with manganese and under-alloyed with nickel, then with optimal parameters, we can achieve functional alloys, and non-optimal parameters, we can, for example, lose in excess manganese, and we can achieve non-functional alloys. And we have shown that we can actually use these for tailoring our material. So we can do some fine tailoring of the Martensite transformation temperature, or we can actually render some zones in the material or final component completely inactive. So for example, there's an example of one of my studies that we have this initial powder amount, and then this S1 sample, which is 10 Martensite, which is the preferred Martensite variant for if you want to actually have a functional nickel manganese gallium actuator. And then we have this S6, which is that's a material which is non-modulated martensite. So in undoped alloy of nickel manganese gallium non-modulated martensite, twinning stress is way too high. You won't be able to actuate it magnetically. So it is actually a passive material, but we can still use it as a magnetic shielding, for example, in a case of a real actuator. Now, how do we get this stuff to actuate if it actually is polycrystalline? So there's a couple of approaches we can take. The foremost approach that usually is used is that we can make the grains crystallographically textured and coarse. So we can make something that is in a sort of a oligocrystal. For example, like this cat sample that we have in the image here. So we can we can have some compositional additions to the material which induce grain growth, for example, during heat treatment, or we can use certain processing steps to induce grain growth. Now, other way is that we can make these grains crystallographically textured, but the material itself can be very foamy. So this is a structure where we have this kind of like tiny single crystals which form like an interlinked structure, and this is what we call bamboo grain structure. And this can also actuate. It's like a metallic form. Usually we use an approach which kind of combines the best parts of both. So we get the force output of the left, but then we get the design freedom of the right side. And this is what we try to achieve with additive manufacturing. And this is exactly what we did here. So this is where we demonstrated the MSM effect in a laser powder bed fusion built nickel manganese gallium. And we made it by making these very thin walls. And when we make it this very high temperature treatment at near solidus temperature, we get this grain coarsening happening. And when we have this grain coarsening, then we could select an area where we could extract the grain for actual testing. So we can actually know, does this material itself, does it have such a defect structure that it would actuate, or would it not actuate? And in this material, we could actually make almost full strain. So we can get this 5.8% magnetic field induced strain, which is with this particular alloy, the theoretical maximum strain is around 6%. So it's nearly maximum theoretical strain. And on the right side, you can see these video clips. The top clip shows actually different twin boundary types we could observe in this particular sample. So we have two different twin configurations. One is the like this normal style twin, type 1 twin, which is very rational plane of twinning. It has a high mobility, but then we also have a type 2 twin, which is actually ultra mobile. So the twinning stresses typically are in the high quality single crystal for type 2. They are in the range of 0.1 megapascal. So the twin type 2 mobility is so high that it's almost impossible to take a good electron microscope image out of it, because the electron microscope, we have an electron gun, and the electron gun generates a magnetic field. The magnetic field generated by this gun is so high that it can actually move this type 2 boundary out of the sample. So very highly mobile boundary. But then also we have this bottom case. This is what we would like for actual actuator, is that we have multiple boundaries, ideally hundreds of them. So we have like more fine twin structure, and this is more stable. The strain becomes very stable, and we also avoid some critical malfunctions, for example, crossing twin structure, where we have like two twins that are actually tilted in wrong direction, and they kind of lock themselves into a place, and it can actually shatter the sample. So that's something we might do in a post-processing step. But now, if we look at the actual twinning values, we actually see that type 1 and type 2 twin boundaries, these mobilities in this material are a little bit lower than what you would expect from a really high quality single crystal. So in typical, I mentioned type 2 is 0.1, then in typical single crystal type 1, it would be in a 0.7, 0.8 megapascal. So we are slightly higher, and this is mostly because of internal defects. And one key characteristics that we observed in this test was that twin boundary mobility might be limited by some volumetric defects in the material itself. So for example, there might be some higher density manganese particulate that might be inside, and it dissipates to the lattice in the heat treatment, and we have compositionally different zone that has a different twinning characteristics. Now, if we want to go from like what could we do if we have this type of samples in the future is, for example, use femtosecond pulsed laser micromachining. So we could make some coarse geometry with a laser powder bed fusion, and then we could post-process it after heat treatment also with a laser like this to cut out these actuating sections. And why we like femtosecond pulse laser in particular is that we have what is process called a cold ablation. So we can cut this or ablate this material without substantial heat input inside it. So we can actually not damage the microstructure or the twinning characteristics with this external process. So we have example here we got from single crystal some this kind of micro gripper actuator, and it works fantastically. And we also shown that if we use green light for the machining itself, we actually have a little bit of better machining performance, and through this process we can actually machine it in martensite, so we don't need to heat it to austenite for the machining process itself. Then other approach we can take is that we can try to get more of this coarse grain structure. We could use epitaxial growth. So this is of course limiting the geometry you can make, because now this epitaxial growth cannot be achieved in any possible geometry. We have some limitations related to it. And in this case, we made something that is more of a thin wall structure, but we tailored the processing parameters in a way that this single track melting pool that we generate, it has this very sloped behavior, meaning that it's not very deep, but it's very wide. And this forces the single crystal or this crystallite to grow in a very defined direction of the thermal gradient. And this way we can make this kind of wall structures where we actually have a crystal Z-axis pointing up during the process. And then in a post-processing heat treatment, those very similarly oriented grains can fuse together, and we can have something that is very close to single crystal. Now, this advantage of this is that those samples generally tend to be very small. So we are trying to find ways how can we sustain similar type of growth behavior in a much larger sample. So we could have a larger single crystal by additive manufacturing. Well, other way we can go at it is something that this is something we have worked quite extensively with Moataz's team. So we have what we call this bamboo grain geometry. So this we don't go directly into foam making, because the foam has there's a huge amount of fraction of this porosity inside them, and that as a full force output of the material will significantly reduce because of this foam. But in additive manufacturing, we can tailor the porosity very precisely. So in this case, we take the approach where we make these lattice-like structures or lattice structures. And we tailor the parameters in a way that we can achieve a very specific strut width. And then in the post-processing treatment, we can do some tricks where we kind of make this structure locally bamboo grained. And this is achieved, we actually show first how we do the measurement itself, is that we have this EPSD, high temperature EPSD. And why we use high temperature is that we want to do these measurements in austenitic phase. Martensite, as you can see, it makes a very complex diffraction pattern, and this is first very difficult to index, but second, it's very difficult to determine what is a martensite colony versus what is actual grain boundary. So by heating, we can actually reveal what is the real grain structure. And now advantage is, of course, that crystallographic orientation of the austenite and the texture of the austenite is perfectly correlated to the martensite. So there's only a 0.3 degree deviation in the axis direction, and it's nearly the same, and from the actuator point of view.
Ville, try to wrap up if you can, okay?
Yeah, I have 2 slides. It's okay. Yeah, so as built, we can see that there's very tiny grains, but then in the post-processing heat treatment, we expand those grains and they fill these narrow struts, and we can get structure where we have kind of this interconnected struts of single crystals, and then these node areas where we have like several grains. And in external magnetic field, this type of structure can strain 6%. In the martensite. So it is effectively a good actuator approach, but of course it takes a lot of tailoring into what should be ideal strut angle and what would be the ideal way to implement the actuator based on this kind of structure. And nice part is of course also that this crystal orientation tends to follow, because of thermal gradient, this actual strut direction, and because of this we have crystallographic texture of austenite, which is then translated to martensite, but also after the heat treatment we don't lose this texture significantly, so we still maintain some primary directions, which of course still should be Poppy modeled a little bit better. So can we manipulate this behavior a little bit more? And this is like short summary. We have a lots of different considerations from the feedstock and processing point of view, and then actually what we can do with the functional material. Thank you.
Thank you so much, Ville. For the benefit of time, I propose that we proceed with the second presentation, and then we can do all the questions at the end just to see if we can, in case people have other appointments afterwards. But thank you so much. This is, of course, very insightful review of the application of nickel manganese gallium. The second speaker for today is Dr. Moataz Hussein, presently at Loughborough University as a senior research fellow. Moataz is another early career academic who has been who are leading a lot of work on additive manufacturing of magnetic materials, in particular soft magnets and magnetocaloric materials. And today he's going to be sharing with us some of the development work he has done in the past on the use of laser powder bed fusion to tame those very complex materials and their processing. Moaz, the mic is yours.
Thank you so much, Moataz, and thank you, Mershid, for the opportunity. I'm Abdelmoez Hussein. I'm working on additive manufacturing, specifically in laser powder bed fusion of magnetic materials. I have been working on several magnetic materials like soft magnets, permanent magnets, magnetocalorics, even superconducting, and I find several correlation between them, even in the failure or even in the successful things. And this is what drove me to talk today about the challenges that specifically I have found in the laser powder bed fusion of magnetic alloys. I'll try to wrap and share the experience that I have found and about the difficulties and the successful things that I have found during this journey. I'll talk about why we use laser powder bed fusion for magnetic materials and the challenges that we find and some suggested solutions. And there is an open-ended question. Probably I can't answer this one, but we will see how probably can interact with these questions. First, why we have to use or we need to use laser powder bed fusion for magnetic materials. Some magnetic materials or some applications need specific designs, which we can make use of the charmic properties of the laser powder bed fusion, which is make a very complex design. For example, like make here as internal cooling channels for some magnetic applications, and even to make some guides for the magnetic flux. So we can make use of the complex design of this of the laser powder bed fusion technique. So these techniques can support, for example, the integrated cooling channels inside magnetic cores. A very good example of this one should be the magnetic refrigeration in the solid state heat pumps. The heat pumps, here where a material you can apply a magnetic field on a magnetocaloric material, the material start to heat up or cool down, and by passing a fluid, there is a heat transfer or heat exchanger can happen between the material and the fluid. And here comes the rule of the laser powder bed fusion process. The rule here is to increase the surface area of the part here as much as we can, so we can increase the efficiency by increasing the maximum heat transfer between them. So we can do a lattice structure like these ones, and this is from shape memory alloys, or even like blocks with channels. And the more complex that we can do, the more efficiency from the device that we can get. As well, we can make use of the laser powder bed fusion in making a directional magnetic properties. If we need to control the magnetic properties in a specific direction, like magnetic shielding, we can use it as well. Of course, it can be used here in shape memory alloys, so we can control the movement according to the magnetic field, and it can be used in defense. And in superconductivity as well, it can be used a very complex design to design radio frequency devices. And as well in aerospace, these radio frequency devices from soft magnets can be used in space as well. So now we know about why maybe we can use the laser powder bed fusion in some magnetic applications and why they need it. Now I'll go through directly to the challenges that we may have it when we process a magnetic material in general. There is two kinds of challenges. First one related to the powder itself once we start to produce the material, and the other challenges when we start to process the material. I'll talk about every item specifically. Let's start with the material related one. Some of the magnetic material during the atomization. Of course, the atomized or the spherical particles will be the preferred particle shape for the laser powder bed fusion. So the question here, all materials can be produced in spherical particles or spherical shape? The answer is no. Some of them, magnetic materials, can be nicely produced, like the one in the left. This is for nickel iron moly permalloy with a minimum of satellites, so the spreadability will be fine. However, this is another magnetic material. Believe it or not, this is a gas atomized one. This is lanthanum iron silicon. Even it has a rocky style particles, and even the spherical one has a lot of satellites on top here. So the first problem that we have, or we can face it, is the powder production itself. How this powder shape can affect the material processing itself. Here is a two example of two magnetic materials, and this is like, this should be both pre-alloyed. You can see how ugly they are, and after processing, the first one can show a lot of defects related to the porosity, or even the cracking. The cracking here is horrible. Probably the crack width is almost like 10 micron widths, or probably 15. The lower one as well, there is a lot of cracks. And unfortunately here, these microstructural defects are not related to the laser processing parameter. This is related to of course, related to the processing parameter, but it's more likely to the flowability of the powder. They are not nicely flowed due to the rocky style, or even the more satellites they have. So they have another defect which is added to the process, and you can't get rid of it, even with changing processing parameters. The second one is oxidation. Is this powder, what's the amount of the oxides in this material? This can be determined during the atomization process. A lot of powder you can just start atomizing without gas, to protect from oxygen. However, the magnetic materials are very, very sensitive to oxidation. Even a very small amount, it can change the material properties. The second thing that I have found also is how many times you are going to use your material. If you use your material for the first time, probably you can get a good magnetic properties from the resultant additive manufactured one. However, from what I found, I was very keen on every build to get the material isolated from the atmosphere and powder storage, and to make it away from oxides. However, what I find that every time I start with the second build, third build, fourth build, the material properties start to be different, even slightly, which is going to have a poor magnetic properties with the recycling. So powder recyclability is another issue that we can find it. So now we will move to the process-related challenges, and the first one is magnetic anisotropy. To understand how the laser powder bed fusion affect the magnetic anisotropy, let's first know what's the magnetic anisotropy. If we have a magnetic material and you apply a magnetic field in a specific direction or another direction, the material start to respond in different way. So let's summarize this as it's a different response of the internal magnetic properties of the material according to the applied magnetic field direction. And this is like hysteresis loop. This is what we need from the soft magnets, for example. And this is a good example from what magnetic anisotropy. So the black one, the material start to saturate when I apply a little bit or small magnetic field. So start to saturate probably at this point 100, and the coercivity is low. So this is good for soft magnet. However, the same material, when we change the direction of the applied magnetic field, it's almost not saturated, and even the coercivity is a little bit high. So how the laser powder bed fusion can affect the magnetic anisotropy? And one of the examples that we face it for magnetic shielding, it was for permalloy nickel iron moly. to make a component for magnetic shielding. So we start normally from powder, pass through the design of experiment, and to optimize the laser parameters, and we find a good condition, which is letter F. Now we achieve a minimum porosity. So let's discover the magnetic properties, which is the logical step. We find that even this condition that has the lowest porosity has almost coercivity of 240 ampere per meter, which is way higher than the commercial one, which should be between 7 to 70 ampere per meter. This too much difference, or this high difference between the commercial one and the additive manufacturing one, should be for a reason. To know what we have, we go for the internal investigation, and we got something interesting from the XRD. So from the XRD, we find that all samples with all different laser powder-based fusion parameters has a rich texture in the 100. And the 111 is almost weak or a little bit low, and this has been also confirmed by the EBSD. To know why this is important information, we find that from the magnetic properties, this alloy, the 100, the high texture is corresponding to the hard axis of magnetization. So this is a magnetic anisotropy that we have. So that's why the material gives us a very high coercivity and the poor magnetic properties, because we have all our samples, the texture has been arranged on the, let's say, the bad axis. So that's why it resulted in the poor magnetic properties. So the solution for this one, we try to make a control for the texture. We try to make or get back the texture to the easy axis of magnetization, and to see, can we manage to do this? So we try to tilt the texture by tilting the cube by 35 and 45 degrees, as we can see here with respect to the Ville direction. And when we have done XRD, we find that the 111 direction start to grow again, and also that has been confirmed by the EBSD. And when we measure the magnetic properties again, we find that there is an improvement on the coercivity from 244, even it decreases to 76, which is very close to the commercial one. So at least we managed to control, by controlling the microstructure, to get very close to the commercial ones. And that was one challenge. The second challenge from the processing viewpoint is the thermodynamic magnetic phase transition. To understand what is this we have, we will have a look on the case study, which is magnetocalorics. Magnetocalorics are materials, they can heat up or cool down once we apply magnetic field, which is used on the solid state heat pump example that we have seen on the first slide. So we were doing some work on these magnetocalorics, and there is a ferromagnetic paramagnetic phase transition, thermodynamic phase transition. There is a lot of phase transition, but we will take the ferromagnetic paramagnetic as an example, and I think it's going to be almost applicable on other thermodynamic transitions. Here we can see the ferromagnetic the spins of the magnetic domain start to be at low temperature in the ferromagnetic state, and they start to be, with increasing temperature, start to get randomized to the paramagnetic state. How this process can be affected? This transition is a very critical transition for the applications that we are looking for. So there is two kinds is associated with this transition. It could be first order or second order transition. The first order transition, this drop in the magnetization is in the first order here. It should be sharp and discontinuous, and it's associated with a heat exposure, which give us the applications that we need. However, in contrast, the second order have a very gradual transition and no hysteresis here, which is associated with probably very low temperature, which is not required for our application. We need a material. When we apply a magnetic field, it can have a first order, so we can have a high temperature response. So we start as normal from powder. The powder was good. It shows a first order almost, as we can see, like a sharp drop. However, when we process it, the magnetization at room temperature, of course. However, when we process using some parameters, we can find there is a gradual transition, which means an indication of a change on the transition. Some of them give like a sudden one, but we will see why they give this one later. To determine the entropy change, which is an indication for the heat that's released from the material, the powder shows almost delta S was number 6 or 6.3 exactly. However, the processed one at room temperature here shows almost 4.9, 4.8, which is almost 70% or 60% from the powder. So we here are suffering from a drop in the properties itself. So here there is an indication of a loss of the first order transition. To make sure that we didn't lose the first order or what's happening inside the machine and inside the material, we start to measure the magnetization versus the isothermal magnetization curves to make sure that what first order we have or second order, what order we have of this transition. So from the powder, we can see here there is a lot of like space here. Also, there is hysteresis. The arrow plot shows a negative slope. So this is a perfect first order, which is getting lost. There is no hysteresis on the processed material, no hysteresis, and also there is a positive. So now we are sure that we already lost the first order to the second order one. So the reasons why we lost the first order, sorry. This is because there is a segregation happen from the material. So this segregation affects the chemical composition of the material. So the starting nominal compositions that we started with has been lost in segregation secondary phases, probably oxides, probably iron, probably lanthanum. So secondary phases are affecting the phase transition itself. The second one is the evaporation, as my colleague Ville has just said that it's very sensitive, even specifically for manganese. And for manganese here we have it. We find that the manganese start to decrease a little bit, and even silicon and even lanthanum. So this is affecting as well the first order transition to the second order. And of course, we cannot deny the oxides formation. And oxide formation normally has an antiferromagnetic nature, which is like opposite the nature of the ferromagnetism that we are looking for. The suggested solution for these things, or in general, we will need to compensate the evaporated elements. This is the first one. The second one, to do post-processing. Post-processing is very critical for some materials. So for example, the lanthanum iron silicon one, we have to do almost 7 days of heat treatment to get rid of the secondary phases that we have, the iron-based and even the lanthanum-based one. So that was very long process, but it's essential to get to the nominal compositions that you started. The hydrogenation, which is heat treatment in hydrogen atmosphere, it's also important for some of the materials because it can break down or decompose the oxides that has been performed or formed during the process itself. So this is very critical. Both alloys and both examples that I have used today has been hydrogenated, has been heat treated in hydrogen atmosphere with a specific pressure as well. In conclusion, there are like two kinds of the challenges. Probably we cannot get rid of all of them or even beat all of them. It's the powder quality, which is something that we cannot control because it depends on the nature of the material. And oxidation, how many times you are planning to use your powder. I believe this will be an important factor that you need to consider. from the processing, the microstructure defect, the cracking and porosity affecting the magnetic properties in general, doesn't matter what it is. The texture anisotropy or the magnetic anisotropy, you can control it and sometimes you cannot, as we will see now. And evaporation, some of the elements are evaporated because they have like low melting point or low evaporation point, and the oxidation during the process itself, and segregation. All of these can affect your the resultant magnetic properties. And now for the question, are these solutions that I have just suggested are global? Can we use it for several materials or all of the materials? My answer is no, because every material has its own specific conditions. Some of the material, like the nickel iron that I have done texture control and magnetic anisotropy, that was a little bit not that hard. However, if we try to apply it for the magnetocaloric, it's different. If we try to do it for the neodymium iron boron permanent magnet, it will be a little bit, not a little bit, away difficult, because the phase is different, and even neodymium needs volatile easily and need to be segregated, or even it's melted within the grains. So my answer would be, the short answer should be no. So we need to investigate a little bit in each material to have its own condition and challenges. However, this is the last statement, and I'm going to end. Some of the challenges should be common. So hopefully in this presentation, I covered as much as I can from the challenges and from my experience. And thank you so much for listening.
Thank you, Moaz. This is great that you give this top level bird's eye view of the problems. I mean, the powder related to heat treatment and other problems within additive manufacturing of these materials. Appreciate it. Thank you so much. Okay, let me proceed with the questions. So the first question is from Kirti Vasan Rajamani, which is for Ville. The question is about the pump and linear actuator. If you can explain how it works, what is that system? You're muted, Ville.
Yeah. I will share my screen again. So
please, yeah.
It will be a little bit easier to explain it with this virtual material. Let's move to the right spot. Okay. Here. So this is the pump application. So what happened? Can you see my cursor? You can still hear me?
Yeah, we can see.
Yeah. Okay, yeah. So we have a MSM element in this. Is basically a modeling. So this is a MSM single crystal on the top, and then this bottom one is the diametrically magnetized cylindrical magnet. So these lines here, they represent how this magnet generates its magnetic field. What is the magnetic field distribution around the magnet? And now when you bring the magnet under this kind of single crystal, you generate this kind of tiny undulation. So basically, in the sections where the magnetic field is distributed along the length of this stick, the C domain or C axis of the crystallographic lattice tries to orient in that direction. And then in the sections where it's more like in 90-degree angle, then the C axis tries to go in that direction. So what happens in the element is that it generates this kind of uneven twinning. And because of this physical kink between different elements, you can see that there's actual physical kink here. These kinks accumulate in a way that it generates undulation. And now when we rotate this magnet, of course, this field distribution will change. So by rotation, this undulation will move like this along the surface of the single crystal. And now if you place here some like liquid/gas tight seal on top of the material and then two outlets, so for example, one like this and one under there, you can use this undulation to travel between these two outlets and move liquid faster. So, and now, of course, if you rotate this magnet into different direction, then this undulation will move to the opposite direction. So it's reversible pumping. You can pump to two different directions simply by switching which direction this magnet is rotating under the element. So that's the basic principle of MSM micropump. So in this case, we would have this driving unit with this magnet under this chip. And then inside the chip, inside the fluid channel, we would have MSM element like that, like tiny piece of metal embedded there. And then there's a fluid channel inside the chip, which can be then, you could have several of this, you could have series of these pumps there, and they could be pumping to different, or you could have multiple different outlets or inlets, or you could have, for example, 2 pumps with different source. You could have one pump that is pumping, for example, water, and one that is pumping oil, and you can make individual droplets which you can sequence then as you wish with those pumps.
Thank you, Ville.
And then this is the linear actuator. So in this linear actuator, you can see that there's some teeth on this metal bar. So the shape of those teeth is like basically like a triangle. And we have a corresponding triangle shape at the end of these metallic bars that are connected to the MSM elements inside these electromagnets. And what happens is that this, it's of course difficult to see from this, but what happens is that this corresponding triangle shape will engage this teeth, but it will gauge it, know that it's not symmetric. It will engage one edge of and it will cause this kind of pushing force which moves the bar to one direction, and then at one point this single stroke motion will of course lose contact with the edge. So at that point this next MSM element will engage the other teeth in the same series, and sequentially like this you can see that they're kind of taking turns to click in. They push this bar to one direction, and then by doing the sequence to opposite direction, then the bar will move to opposite direction.
Thank you, Ville. I have a question now for Moaz. Did you evaluate the relative cooling power values compared with the gadolinium-based compounds?
Can you repeat the question, please?
That's for Moaz. Yeah.
Sorry. Yeah. Okay.
Yeah.
Yes, let me share. Yes. For the relative cooling power, it's just to identify it for the others. It's a multiplication between the maximum magnetic entropy change and the full width at half maximum. There is 2 things about the relative cooling power. The first one, it received in spite it's like it has been used a lot in publication, but the first one, it also in parallel, it used a lot of critics in using it and comparing or to express the quality of the material in terms of magnetocaloric. This is because the material, for example, can show delta S of 2, but it has like a wide range, like the full width at half maximum, it's very wide. So it has a very critics. This is the first one. The second one, for gadolinium, it is the ultimate, of course, the benchmark should be the benchmark for magnetocaloric. I agree with this one. So I think to compare it with this one, we need to measure the delta T, adiabatic temperature change. And we already have done this one. And for our material, we find it gives 1.4 Kelvin at 1 Tesla applied magnetic field. This is still below the gadolinium, of course, because gadolinium, as I mentioned, it's considered at the benchmark. However, we are trying to replace the gadolinium with other materials. Like 1 kilo of gadolinium, I think probably it's $4,000. So we are trying to replace it with another cheaper material. So the short answer should be, we compare the adiabatic temperature change, which is 1.4. It's almost around 45% of the gadolinium. Hopefully we can make some changes to get this number high.
Thank you, Moaz. There's another question about cycling.
Yes.
About the cyclic response. Yeah, cyclic response of magnetocaloric materials.
For magnetocaloric, what is the minimum printing size realistic possible? It depends.
No, there's a question before as well. Did you also measure the cyclic response?
No. We didn't. We hope to measure this one, but I think it takes a lot of time and a lot of the material itself. I mean, according to the shape of the material, the internal shape of the microstructure, I wouldn't say it will survive for a lot due to the powder shape, the rocky things and the satellites. So if you try to magnetize and demagnetize, it will go to a point where it's like the material start to probably cracking or damaging, because there is a lot of stresses as well come from the applied magnetic field. So as well, the short answer would be we didn't try it. However, we believe it wouldn't survive for at least 4,000 cycle. So this wouldn't survive to 4,000 cycle, which is also the benchmark for gadolinium as well.
Okay.
The second one.
One last question today.
Yeah.
For magnetic alloy materials, the minimum printing size possible. So
it depends on the it depends on the probably the machine and the process and a lot. I think a lot of factors can answer this question. The machine tolerance, probably the powder size, probably the scan strategies, probably a lot of things. I would say what the minimum that I have done with this material is we have done a pores in 400 micron, and the designed one should be like 410. So it was almost 10 micron difference. So this question should be, as I mentioned, a lot of factors related to not to the physics or the science. It's related more to the processing
itself. Yeah, I can add, obviously, most laser powder bed machines, as you know, they have a spot size of around 60 micron, but that's the spot size. The pen you're working with is probably like maybe almost 100 microns. But there are some new machines like 3D Microprint, GmbH, the German company, who have spot sizes that can go down to 30 and even 20 microns. So that means that your pen becomes smaller. But of course, if the pen becomes smaller, then you have to fill with a lot of hatching to be able to build the shape. Okay, now I return back the mic to Mershad to give his comments and thoughts about this.
Yeah, thank you very much. Thank you very much, Moataz, Ville, and Moez for very nice presentation. Moataz, specifically you for hosting the session. I really enjoyed. I also have a couple of questions written here, but I know about the time, so I keep it for maybe next time or contact the speaker separately. Like the other webinars, definitely the video will be shared later on YouTube, and I share it also on the LinkedIn page of AM Smart. The only point I would like to mention is the upcoming conference. So AM Smart is going to have a conference in September, first conference on additive manufacturing of smart materials at University of Twente, 14 to 16 of September. More information will be shared in upcoming weeks. However, the information is already available on the website of the conference and amsmart.net. If you are interested or are available for that, please, you are welcome to join and visit also our center or all facilities. Yeah, that would be great to also have you around and also have a bigger community to listen to your presentation. Having said that, thank you again and wish you all very great day, night, or evening, wherever you are, and see you next time.
Thank you. Bye-bye.
Thanks, everyone. See you soon. Thank you. Bye-bye.
Bye.